Data and transaction security is essential to all digital operations. With its decentralized network, blockchain has a different way of maintaining and guaranteeing its data security, which different from the centralized system. In blockchain, the mechanism of safeguarding data and transactions is called a consensus mechanism or consensus mechanics. The consensus mechanics is a fault-tolerant mechanism used in blockchain systems to achieve an agreement on the value or authenticity of a transaction or data. This is necessary to verify the identity of all individuals or parties involved in mining activities and transactions. There are different consensus mechanics being applied in blockchain, including proof of work, proof of stake, and proof of capacity. Usually they're referred to by their acronyms, so POW, POS, and POC. So we will examine this subject closely with Blockchain Zoo CEO Roberto Capodieci. Good morning, Roberto.
Good morning. And this is a very interesting topic. There is a lot of demystifying to do. There is people, because there is a complex things, many people tend to treat it like a religion. So they believe in proof of work above the logic reason why it should be considered good or not, and so on and so forth, also with proof of stake and the others. So a lot of clarification to do and a lot of things to understand about consensus algorithm, consensus mechanics, or whatever they want to be called.
Okay, so what are some of the misunderstandings, the most common misunderstandings about consensus mechanics? And you mentioned like people being fanatic to like certain measures of this safe security.
Well, no doubt that when people don't understand something, they give it a sort of a need of a faith, right? Like fire, there was a god or the sun is God until the science explain it, right? So with the consensus mechanics, it's important to understand how they work, why they work well or not, before devoting yourself to one. So first, the things that need to be understood is that the word consensus can create a little bit of a confusion. While between human consensus is achieved by sitting around the table and discussing and finding a point of agreement, let's say where we go to dinner tonight, and then we sit and somebody proposes a restaurant, the other says no, until I don't like fish, I'm vegetarian, until one choice in common is done. In a peer-to-peer network, consensus cannot work like this. The nodes cannot sit around the table and discuss. For the first principle that peer-to-peer network, each node doesn't know the extent of the network. So in a peer-to-peer network, each node has no idea how extended, how many nodes are there. Each node only knows the one that it talks to. So there is no way that the nodes can sit and discuss and find the consensus. So the consensus mechanism in a peer-to-peer network is a preset rules in each node that apply to a possible choice. So when each node has a choice to make, looks at these rules and make the choice based on the rules. Because the same rules should be identical for each node, then you know that all the nodes are going to make the same decision, so they are in consensus about a situation. Things like, is a transaction legitimate or not? So because the transaction is presented to the node, then the node look at the rules and say, okay, this transaction is legitimate. The outcome is this, the rules are the same, so all the nodes are going to come out with the same result. And this is one of the basic aspects of how a consensus works. But if these rules are not coded properly, a consensus can be gained by somebody that wants to trick the system and do the biggest nightmare of cryptographer, which is the double spending. So in a case of a blockchain with cryptocurrency, if I can pay somebody with some funds and then get back the funds in my account and pay somebody else again, I am double spending, and this should never happen. So the consensus should be programmed well enough that this will never happen. That's
So like first of all, like the term consensus here is not defined in the way that we understand it in a day-to-day life, right? So this doesn't mean like people talking together to reach an agreement. This refers to like a preset rule written to govern the nodes in the blockchain. Yeah. So like who write the rules actually? Is it like all the node participants or yeah?
This is a good question. The rules are written by the developers that create the core software for the node, right? It can be open source community, it can be one architect that design, other people codes. Proof of work, which is the most famous because it's the one used in Bitcoin, it is a system that comes out from something that was developed in order to prevent spam emails. There's a strange history behind proof of work. Proof of work forces a processor to do a lot of work before obtaining the correct result. And it's based on this in a cryptographic function, which is the hash. The hash is a mathematical result given an input. The input can be a piece of text, an image, whatever. In case of the blockchain is the previous block. Process with this mathematical function create a string, always of the same length, that in binary system is made by 1 and 0, can be 101, 100, whatever it is, okay? So the trick is now to produce an hash that starts with a certain amount of zeros. So the difficulty is to modify the input source and keep trying to modify, because this function is one directional, so you cannot create a source from a result, so you can only create result from source. So keep changing the source, adding a small number, 1, 2, 3, 4, 5, whatever it is, so that the output, the hash, start with 0, 0, 0, 0, 0, 0, whatever is the amount of zero is what is called difficulty. So what in Bitcoin, let's say there is a high difficulty, means that the hash, in order to be considered valid by the consensus, need to have a certain amount of zeros at the beginning, which means that the trial and error to find this is a big amount of trial. So this is the basic of proof of work, but this is one. So to consider a blockchain valid means that each next block need to have the hash of the previous block with a certain amount of zeros. This makes it sure that before somebody can create an alternative blockchain, they need to compute faster and with more zero than the main blockchain. In this way, if somebody want to double spend, need to spend first in the main chain, then start creating an alternative chain that has more zeros, where it removes the transaction where it spent, so that all the nodes in the blockchain see that there is a blockchain with more zero, which the consensus of proof of work consider better, abandon the one that they had where he actually spent, and adopt the one that the hacker, let's say, created, where his expenditure is not there. The transaction where he spent the money are not there, so he still have the money with him. And this is happen when somebody went to an exchange, deposit proof of work cryptocurrency, withdraw another coin, then create a blockchain alternative chain with more zeros with a higher difficulty. The proof of work chain choose that, and the money that he deposited in the exchange are back with him. So the exchanger paid out some money to him, so now he doubled his money. And practically this is the nightmare of people that code consensus system. So the good consensus should not let this happen. So there is what is called 51% attack. So somebody able to produce a better blockchain than the rest of the network.
Okay, and that's the proof of work, yeah. So what is, like, how does the proof of stake work?
Okay, that's a good question. So personally, I divide the consensus mechanics in two different categories. One, they use external sources to validate the quality of the blockchain, like proof of work, use computing power. So anybody that can put together enough computing power can overnight become the most powerful and produce an attack. Then the one that use past history data of the blockchain to secure the blockchain. So doesn't matter how much money somebody has to purchase computing power, for example, for proof of work, for an attack. In a blockchain like proof of stake, you need to have a past history that justify your power to be the one creating new block and then do the double spending. In the theory, proof of stake is also vulnerable and is defended by the fact that in order to produce an attack, you should be owning 80%, 90% of the economy of the blockchain. So let's say the blockchain has 1 million coins. You need to have 800,000 coins to have enough stake to be the one that always create the new blocks and then be able to create a weaker chain as a main chain and then propose a better chain so the node goes to the better chain, right? But in this case, the only person you damage is yourself, because the idea is that the attack is done to the cryptocurrency of the blockchain itself, right? So in this case, the defense is not the fact that an attack is impossible or difficult. There is another theory that because it's based on history, if somebody goes around and purchases the private key of people having good balance at the beginning of the blockchain, can also using these keys to produce another history that is... but those are legends, because proof of work attacks happen often and they're done often, while proof of stake is just on paper in theory. No proof of stake blockchain there is record of ever being subject of a double spending attack or is called reorganization attack. There is to consider though that is the security based on the value of the coin, then even a proof of stake blockchain is safe when it's protecting its own coin. But if it's used to manage title, for example, NFTs in this case, which are, for example, of big value compared to the market cap of the blockchain. So the market cap of the blockchain is 10 million, but I'm managing art pieces and NFT that are worth billions. Then an attack makes more sense, because it's no more to defend the cryptocurrency of the blockchain, but you need to defend titles that have a value that is bigger of the value of the coin, which makes it vulnerable to, so it makes sense to do the investment to make an attack, let's say. So also proof of stake blockchain at a certain point are weak in the theory again, because in practice it never happened, to this sort of attacks.
Okay. And what is proof of capacity and how does it work?
Proof of capacity usually is used in a chain that offer decentralized storage. And there is a way to people claiming which is the dimension of their hard drive, and there is a function that fill up the empty space of their drive and produce a certain result. That is only possible to produce if you have the actual capacity in your hard drive. So based on the space that you are then renting out for storage and the space that you put available in the blockchain to be filled up with space for storage, you gain a certain power, so you have a certain right to create block, a certain precedence to create block. This belongs to the category with external source, because I put a data center over drive and suddenly I am the most powerful node in the blockchain and I can create all the blocks, so I can do attack of sorts. So whenever you can just purchase what gives power to you is a matter of investment. So does the attack worth the investment? If yes, then you know, people can purchase whatever it costs to perform the attack. So when attack is based on external sources like computing power, hashing power, storage, processing power, people can always put the money to purchase these and gain power inside the blockchain.
You mentioned attack several times, like usually what kind of attack, how happen in the blockchain system? Like, are there some illustrations or examples?
So the classic is the double spending, right? So as I explained before, let's say I purchase, it happened a few months ago, for example, in the Ethereum Classic. Ethereum Classic is one fork of Ethereum. Actually, it should be the original Ethereum if somebody want to consider it technically. And which is in proof of work. His coin is valued, but there is not much people putting hashing power to protect the blockchain, right? So it's proof of work. Somebody purchased $1 million worth of Ethereum Classic, okay? So they have $1 million worth of Ethereum Classic, they go to exchanges, they deposit Ethereum Classic, and they withdraw Bitcoin, okay? So at a certain point, they don't have any more than $1 million Ethereum Classic, and they have $1 million of Bitcoin. Then they take $100,000 and they rent a lot of hashing power to have the majority, a good chunk, like 80% compared to the hashing power used to protect Ethereum Classic, right? At this point, they're gonna write an alternative blockchain that replace the blocks where the guy deposited his Ethereum Classic in the exchanges to withdraw the Bitcoin. And he writes this new piece of blockchain with much more zeros at the beginning of the hashes between each blocks. And this makes so that every node of the Ethereum Classic blockchain see this alternative blockchain, see that it's better, abandon the one that he had where there are the transactions where he deposited $1 million Ethereum Classic in the exchanges, and adopt the one where he didn't. So at this point, the guy has $1 million Ethereum Classic back with him because the transactions that he used to deposit in the exchanges are gone. But he has also $1 million of Bitcoin that he withdrew before. So he doubled his money because he managed to delete the payment, but he already got the good. So let's say if it was NFTs, and I pay for an NFT, for example, in the moment that I can rewrite and remove the payment, I get the NFT, but I still have the money that I used to pay, for example. So this is the function, the basic function of a double spending is the classic attack on a blockchain.
Okay. What are other security issues in blockchain transactions?
It all boils down on how things are coded.
Okay.
So if the core system is not programmed well, people find faulty functions in transactions so they can add the payload in the transaction that crash the nodes. We need to consider that for how the peer-to-peer network works, once a broadcasted transaction, this is copied in all the nodes. So if all the nodes are running the same software, automatically if somebody finds a faulty function in transaction that can create the nodes to block, to stop, suddenly with this transaction, all the nodes are gonna stop, so the blockchain stops. And it happened quite a few times, and then people fix the code, release an update, and the blockchain restarts.
Okay. So like, again, like, coding is a really essential part. Yeah, blockchain transactions, yeah, including in terms of its security. And then, like, how do you verify the identity or the authenticity of like people or documents which are involved in a transaction blockchain?
Blockchain generically, unless is coupled with the KYC or an identity to connect a physical identity to an account, the identity are limited to the account. So what an account does, you know which account did it, but you don't know who is behind the account, pretty much. And a peer-to-peer network also make it difficult to triangulate the source of the transaction, right? Because it can be posted in any node and is propagated. So there is the need to own enough nodes and being lucky that, let's say, law enforcement want to find somebody spending Bitcoin that came from a crime, a ransom, or whatever. They need to own enough nodes in the blockchain and being lucky that the broadcast goes very close to their nodes to start to triangulate where the source is. But without this, it's pretty much difficult to define the source unless there is the cooperation of the node owners of the node, administrators.
Okay. But then how does security protection measures in decentralized networks differ from security measures in centralized systems?
Sure. I think that the biggest difference is that in a centralized system, the security are more technical. Mm-hmm. So means firewalls, means the code that has to be strong, whatever, operating system, etc., etc. Because behind there is everything. Okay. While in a decentralized system, the security is all based on logic. So protocol level. So the protocol need to be designed so well that it doesn't have logic flow. Because the attack on a decentralized system is always based on logic, which boils down to code. But code can be perfect if the logic is faulty. Even if the code is perfect, you can game the system.
Yeah. And I read somewhere that with the centralized system, because like they have only like one source of not power, like source of operation, or like one central server. So like once the server is taken down, then the whole system will go down. But then I read somewhere that with the decentralized system, that you have, if somebody managed to attack some of the nodes, then the other nodes will stay intact. Is that true, or do you need to clarify on that?
The idea of how a peer-to-peer self-heal and self-organize. So there is one protocol that is really at the peer-to-peer level. So it's not even the blockchain protocol, it's just how the nodes are managing to be connected one with the other. Mm-hmm. And they have a sort of tolerance. Consider that there is no global truth. So each node has its own truth on what sees and what believes. But if one node is talking with 20 other nodes, which is the average amount of connection that they can keep simultaneously, and one of these other nodes is always saying something different compared to the others, or it goes offline, is not reliable, you get blacklisted. Get blacklisted and give it a certain amount of time to be given a new chance of behaving properly. And then you misbehave and the blacklisting is longer, and so on and so forth. So in this way, each node keeps his own list of what nodes to trust. And in this way, nodes that misbehave are left away. So this is also though the cause of what is called forks. So if let's say there is an update in the software, or for some reason half is attacked with some changes, the nodes start eliminating the trust on each other, creating two subgroups. So from one large network you get two smaller networks, and each network still living their own life, their own truth. In case of blockchain, then you have two different blockchain forking from a single one, because some node consider the next block correct, the other not, because maybe the rules on how or what to see correct is different. And this sometimes is caused not even just by the code that the people write for the blockchain or for the peer-to-peer, but is given by the operating system where this software runs. Let's say the operating system is tolerating a certain mathematical function, and another operating system is not, because it's 32-bit, the other is 64-bit. Maybe the result of a transaction is different, half of the network from the other half of the network. At this point, they split into subgroups. So and this is another very big risk when running peer-to-peer network or blockchain systems.
Okay. And this might intersect with my previous question, but what is the biggest challenge in terms of blockchain security nowadays, and what are the latest innovations in order to make it better?
I do believe that there are two different kinds of challenge. One is on the bottom level, which is the code and attacks that are going in the bottom level, but one is also in the top level, is where the user interface with the blockchain. Because I can attack a blockchain in its core functionality, but I can also attack a user by creating a fake wallet. where people put their keys and then I steal their funds through the attack. So there is a full ecosystem that goes from the user. Let's say you download the fake home banking, internet banking application in your phone. You put your actual password and the hacker uses this to log in to the actual bank and steal your money. So you have the similar challenge when it comes to blockchain, with the fact that it's not even regulated, so it's much more harder to. So you have these two layers of the user interface, the user experience, the connectivity, and one layer underneath there is the code, the attacks that happen in terms of servers, network, etc.
Okay. I think that's all from me. I mean, from my side, I think I've asked all my questions. Do you have anything else to add?
I think it's worth it to understand the consensus mechanics as a general culture things, and don't just devote yourself to one because you think is good and the other automatically are bad in a sort of a religious faith toward proof of work because it's the only. There should not be any other cryptocurrency except Bitcoin, and this is a little bit illiteracy, right? Okay. So I do believe that there is worth to understand more and learn more about consensus mechanics. In the first volume of the series that we wrote your book, there is a huge section about all the consensus mechanics. Probably we can leave a link to download the book or purchase the book on Amazon on the bottom of the video. But I think every person that is into cryptocurrency, is into blockchain, should devote at least a little bit of time to understand how the system that they like so much and they use so much actually works.
Okay, so because like each mechanism has its own strength and weaknesses here, so and then it depends on the context, like case by case, so it's not a one size fits all kind of remedy. Okay, and then like of course, like in the description to this video, like we also add like some more information on how you can buy the book through Amazon, and then you can find it in the description box in this YouTube video. So that's all for our podcast session today on the security of blockchain system. So thank you for tuning in. If you have questions, please leave your comments on the comment section below, or if you're listening to this on Spotify or through the website, you can also leave your comments and questions on the website. And if you'd like to suggest a topic that we should discuss in the future, you can also leave us a message. So thank you and see you next time.